In earlier presentations, we have found that we can represent our system model with a filter, a digital filter. So, one important question now is how we can determine our system mode parameters from the filter coefficients of the digital filter. And this is what we are going to deal with in this presentation. So, to solve our mode parameter estimation task, we have sort of determined digital filter coefficients AN and BN, such that when we feed the filter with the exciting 4 sequence, the filter output approximates the system's response sequence as closely as possible. So our filter coefficients AN describes the denominator polynomial of the system's transfer function in the Z domain, whereas the filter coefficient Bn describes the nominator polynomial. So, how can we determine the mode parameters from these filter coefficients An and Bn? Well, if we start with the system poles and the transfer function, return to the transfer function like this, and we reformulate this then as the denominator polynomial, P in the denominator and N the nominator polynomial. Then the denominator roots. If we find the roots Z1 to Zp, the maximum number of, well, the number of roots is, since the denominator is a p-order polynomial, we have exactly p roots. So the denominator polynomial can be formulated in this way if we use the factorization, the factor theorem. And all these factors then equal to 0 defines our denominator roots. So the question now is, how are the denominator roots related to the system poles? Well, in order to find out that, we have to look closer upon the relation between the Z transform, the Laplace transform, and the discrete Fourier transform, because the relation between these transforms gives us an indication on how we can calculate the poles from the roots. So, to start with, the Z transform of a sequence xn can be formulated in this way, in this series expansion. And if we continue then with the discrete Fourier transform of the same sequence, it can be formulated in this way, where we now have the exponential raised to the power of minus I omega n, where omega then is the angular frequency. And if we reformulate this slightly, we find that we can write it in this way. And now we can see here that the Z variable here is related to e raised to I omega. And that is the relation we will use to go from the roots of the denominator polynomial expressed in Z to our system poles. Because in the Laplace domain, Z then corresponds to the exponential raised to the power of s, where s is the Laplace variable. So the roots Zn can be expressed in this way, and Sn here is the system poles we are looking for. So if we solve for the system pole, we get this relationship. So if we take the natural logarithm of the denominator roots determined from the Z domain version of the system transfer function, and then take a minus sign of that, then we get the corresponding system pole. Well, this is not completely true, because it can be found that we have to multiply this with the scaling factor. So where does this scaling factor come from? Well, it is because we assume, in the processing of our filter functions, we have assumed that the impulse response function sequence is sampled with 1 unit time increment. In physical terms, with 1 second time increment. But this is not true in an actual measurement. So in order to get correctly scaled poles, we have to multiply with a scaling factor that is equal to the sampling frequency. If we do that, then we get correctly scaled poles. So this is the relationship we have been looking for. The system pole corresponding to a denominator root is obtained by taking the natural logarithm of the denominator root and multiplying with minus sampling frequency. And can be found then that when we do this, we will find that all poles appears in complex conjugate pairs. So if we find one pole, then we will find its complex conjugate as a pole as well. We can also find that if we select an impulse response function measured in another observation point, then we will get the same set of poles, exactly the same set of poles. So that means that the poles is a global property. It will be found in all observation points. The same set of poles will be found in all observation points. There is only one exception to this rule, and that is if we have observation points on a nodal line of a mode, then the pole of this particular mode will not be found. The mode shapes then. How can we find the mode shapes? Well, if we have determined the poles with the method we described on the previous slide, we can determine its Laurent series expansion. So we have the system transfer function like this, and express it as with the factor theorem like this. Then it's a fairly straightforward manner to use a rational fraction expansion and express it as a sum of fractions like this. So for each pole here we have one fraction, and the factor in the denominator here is known as the residue. So R1, residue 1, corresponds to pole 1, and RP corresponds to the root ZP. And it turns out also exactly like the system poles, the residues appear in complex conjugate pairs. And all these complex conjugate pairs is of course due to the fact that the impulse response function must be real valued. That is the reason for these complex conjugate pairs. Okay, back to the mode shapes. It turns out that the residue R and K, the residue corresponding to pole N, measured in observation point K, is proportional, directly proportional to the mode shape component corresponding to pole N and observed in point K. So we can formulate our rule like this, that the kth component of the mode shape for mode N is a constant times the residue for pole N observed in point K. So we can simply determine the residues for all observation points for mode N in all observation points K, and then select this scaling factor arbitrarily, depending on what kind of normalization we use for our sets of modes. This means then that in contrast to the system poles, we need to determine the residues for the mode for all impulse response functions that we have measured. So for each observation point, we need to determine the residues for all the poles. So if we want to formulate kind of step-by-step method to determine the mode parameters from the filter coefficients, we start with determining the impulse response function in a set of observation points. Then we select one impulse response function, preferably one which does not use an observation point on mode's node line. Then we determine the filter denominator and nominator coefficients, that's the A and Bn coefficients, for this selected impulse response function. Then we can determine the system poles from the denominator roots. And given the system poles, we expand all the transfer functions in the Laurent series. And from the Laurent series, we get the mode's residues, from which we can determine the system's mode shapes. And that's all. Now we have completed our mission.